to the first section, which is exploring the programming world. So what are we going to be covering in this section? In this section, we are going to be seeing all the stages involved in developing a computer program. And what is programming in the first place? So this is just a process of telling the computer what to do, and we do that through instructions. So with the instructions that we give to the computer, it either solves a problem or runs a program. There are 6 stages involved in developing a computer program, and you have to understand all of these stages. So we're just going to be having an overview of these stages. So the first stage is understanding the problem. So like John Dewey says, the problem well stated is a problem half solved. It's the same in computers. So if you don't understand the problem very well, firstly, like a human, before trying to see how you'll be able to instruct the computer on what to do, then you will not be able to solve that problem. So you have to take your time and understand that problem detailedly as a human first, before you start seeing on how you'll be able to tell a computer on what to do. And when you're understanding, you have to break it down to all the steps possible. You don't have to skip steps. You have to break it down, because there are those steps that you have to use to tell the computer what to do. So can you imagine that you are planning on building, or you build a river without calculating the river's width? Just imagine what can happen. So in programming, unclear goals will result in buggy or inefficient solutions. So when we mean buggy in programming, we just mean code base or a program that has issues in it. So now, what are the key steps that are involved in understanding the problem? So let me just list all, and then we start with the last. So let me get this homemade stylus here. So here, the first step that I want us to look at will be uh, asking the stakeholders. So the stakeholders here can be the client, the person that you want to build the system for, or you can still be yourself. So you have to ask questions like, what is the system going to do? So with this feature, how is it going to function? How will the user be able to interact with the system and stuff like that? So an example can be, the stakeholder can be like, I want a system that users can create their accounts, and with their accounts they can maybe post what they have to sell, and people come and create their accounts and purchase what the other people have posted. So let's just take that example. So that will be a user stories. So after you have understood the problem, what do? You start defining the inputs and the outputs. So let's say creating an account with the authentication system. Let's focus on the login alone. So you see that with login, the inputs that will be required will be the username and the password of that user. Then the output will be either the user will be authenticated if the user is a registered user and the credentials that they have provided are valid. Then if that's the case, then you grant the user access. But if that's not the case, you revoke or you deny access for that user, because that user is not identified. Then now, after they have to identify constraints. So with the constraints, we'll have to user-centric and technical constraints. So for the technical, you'll be focusing on the stress that the system you'll be focusing. So with the technical constraint, you'll be focusing on the processes or the type of processes that the user. So let's look at the technical constraint. So here we have something like must process a million requests per second. So that's one of the technical constraints that you can have, that the system is required to process a million requests per second. Or for user-centric constraint, that here the interface must load within 2 seconds. Let's say the website must open within 2 seconds. So that will be some of the key steps that you will need to follow, so that you can actually understand the problem. Then now, after you have understand the problem, what you will need to do is plan the logic. And here, this part is very crucial. Remember, if you don't plan the logic very well, or skipping a step can cost you a lot of setbacks and lead to a lot of time wasted. So with planning the logic, you don't skip a step. You have to align all the steps well, so that when you start coding, you just follow the steps that you have aligned, knowing that if you don't plan the logic very well, you always be going back and forth, and that is how it's going to be time costly, and it's going to be uh, expensive too. The cost of the project will both increase financially and time wise. So tools and techniques that you can use to plan the logic. The first one that we'll see will be pseudocode. So with pseudocode, it just involves writing code in plain English or in your dialect if you choose. That's pseudocode. So here we don't focus with a complex programming structure. We just implement, or we just plan the logic with simple English. For our case, we just use simple English, and then with a little bit of code-like structure, just a little bit. So the next technique will be flowcharts. So here we just use symbols to visualize logic. So an example of a symbol will be diamond like this. Oh, this sounds really disturbing. So it will be a diamond. It will be a diamond, and now with this diamond, it will be used for decision making. As we go on, we'll not focus on flowcharts a lot, but we'll take a few examples and visualize them using flowcharts. So now we have algorithm techniques that we'll see as we go later on. Then there is something that you have to take into mind: time versus space complexity. It is very important, especially time complexity. So with time complexity, it just focuses on how efficient or how fast your program runs. Then with space complexity, now it focuses on how your program consumes memory. So memory here, we're not talking about your drive, your secondary storage, maybe a hard drive. We're focusing here now with the RAM. So as a program is executing, all the instructions and the data required to execute that program is stored in the RAM. So if your program is memory efficient, you say your program is going to run, let me not say really fast, the program is going to be very efficient. So now let's go to the next step, which will be coding the problem. So after you have identified your problem, after you have understood the problem, and after you have planned the logic, the next step will be coding or converting the logic that you planned in plain English. Using, now you have to convert. So after you have identified the problem, you have understood. So after you have understood the problem and you have planned the logic, the next step will be coding that problem. So here now you are going to be converting the logic you plan into code using a programming language that best fits the problem that you have identified. So some of the programming languages that we will study will be C, C++, Python, Java, then we'll go to JavaScript. So it just depends. Let me see. We'll study C, C++, JavaScript. Then from JavaScript we'll go to the web, and if we have time we can go back to the other programming languages depending on the time. So now clean code is maintainable and scalable. Just start taking note of these terms that I'm mentioning here, because I'll be referencing them a lot, but as we go on I'll start explaining them too better. So messy code is like a tangled necklace, hard to untangle and easy to break. So what are the best practices that you have to consider as a programmer or as someone starting? So readability is key. So you have to use descriptive names for your variables and your function names, and you have to add comments to complex logic. So as you start building, you discover that you might code something here today, and in a week's time you don't even know what you were doing there. You're like, what was I doing here? So how descriptive names of variables and functions is going to be important is that you might see a variable name or a function name and you're like, oh, this function is expected to do this. Let's say you have a function name like sum. So you know that the end result should be that you should take in two, let's say a minimum of two parameters, or you should take in a parameter and return a sum. So just with how descriptive the name is, you can start remembering what that function was doing. Now comments are very important. So when you try to implement something that is not obvious or that is a little bit complex, you have to comment it so that you coming back to that code base later on, you have an understanding of it, and anyone that opens that code base will understand what you were actually doing there. So one of the best practices that we're going to look into will be modularity. So code bases are going to be very big, very big. Let's say just authentication alone, just users creating their accounts, being able to log in, be able to log out, be able to change their password, forgotten password, and you verify maybe their emails, their contacts. That is something that is very huge. It's big, and you span thousands of lines. So what do you do? Modularity here, you can be like, okay, creating accounts, I will split that into a function and go and implement it. Then logging in, that should be a different module or a different function on its own. Then now you just import now these modules that you have created into maybe a main file. I want to use them there, and anywhere you need that functionality, you can always just import and use. So what modularity will do is that it's going to make the code base maintainable, and it's going to make the code base or some functions or some components inside the code base reusable. So modularity is going to be key, and we're going to look into that as we commence. So translating the program to machine code. So after you have coded the program, what you will need to do now is to be able to translate that program into machine code. So these programming languages that we're going to be using, they are high level programming languages, and computers don't understand them. Like for example, we have statements like print in Python, or printf, or cout, or console.log. Those are high level commands that only us humans can understand. The computer cannot understand that. So for the computer to be able to understand that, it has to be translated to machine code, which is just ones and zeros. So now let's look at the ways our programs in our high level languages are going to be translated into machine code. So the first thing, or the first step we're going to look at, will be compiled languages. So I have languages like C, C++, those are compiled languages. And what is compilation? So this is just a process of bundling the entire file, or let's say, yeah, let me just say file, the entire file, then converting it into machine code at once. So you bundle, or the entire code is being converted into machine code all at once. So now with compilation, it is fast in the sense that after the code has been converted into machine code, what happens now is whenever you need to execute that program in that machine, you just have to click the executable in case of Windows. Once you compile, an executable file is being created that whenever you want to execute, you have to click the executable and the program runs. Now the issue with compiled languages is that it is difficult to debug. It's difficult to identify issues. It's very difficult. So let's say you have something like, now with issues we have two types of issues. We have semantic and syntax issues. So with things like syntax issues, it will be easy for our compilers or for our IDEs, integrated development environments, to be able to identify these issues. But now with things like semantic issues, it's going to be very difficult to identify. So let's say you have an entire program that, or let's just say, calculates or performs calculations, and there is somewhere that you do a semantic error, that you divide something by zero. What happens with compile languages? Once you execute, once you compile and that executable is created, you execute, and whenever you reach that point, the code base is just going to break, and you'll be like maybe non-zero division and stuff like that. So once you have that issue, you don't even know where it is coming from. So you have to open your code base and start checking where is this issue coming from, because once it reaches there, your code is going to crash. But now let's look at interpreted languages, and then I'll relate it to this scenario. So for interpreted languages like Python, what happens is that during execution, the code is converted into machine code line by line. As it executes, it's going to be converting that line of code into machine code. So in case of a zero division, what happens? As it identifies that runtime error, what happens? It just stops execution and it stops on that line, and you can easily identify that this issue is coming from here. So maybe this variable at a point in time can be 0. So what do? You resolve that there. But now with compile languages, you will not know where it is, so you have to start debugging, looking for where that issue might be coming from, and it can take you hours upon days, maybe even weeks. Thank God to AI now that you can be like maybe trying to use it to identify where the bug is coming from. So now, interpreted languages are slow in the sense that whenever you want to execute a program, you have to open the code base and you start interpreting line by line. If you compile languages, like I said earlier on, the entire code base just converted into an executable file that you just have to come and click and it runs. But the advantage that we have seen is that they are easy to debug, very easy. So now let's move to the fifth stage, which will be testing the program. So once you have coded and you have compiled, you have to run the code and actually test for problems like what? Like semantic errors. Remember, with a semantic error or with a runtime error, your code base can or your program can break because of such errors. So for things like semantic errors, now this will just be errors with your logic. Maybe you're not following some of or so this will just be errors with your logic. Maybe your logic at the point in time is flawless. Maybe your logic at the point of or maybe so with semantic. So let's look at the fifth stage. So let's look at the fifth stage, which will be testing the program. So once you have compiled or once you have translated your program into machine code, what you have to do is that you have to test, make sure that your program runs and the expected results are being met by your program. So remember that a small bug or a small issue can crash your entire system. So now there are several test layers that we should look into. So we have something like the unit test, and here you just be testing the individual models if their business logic is being met. Then for integration testing, you integrate the different modules and you test if they work well together. Then stress testing, and with stress testing here now, we're focusing on the reliability of the software under pressure. Can your system withstand 1,000 requests per second or 1,000,000? So that's where stress testing will come into play. So once you have tested and your program is okay, then you are free to go to production. But there are some things that you need to know before you push